Sure. Okay. Thank you. And let's move on to the next session, and it's going to be a deep dive on the power architecture by my colleague Satish Kumar Sadasivam. And Kumar Sadasivam is a senior performance architect who leads the workload characterization and future architecture design space exploration team in IBM. He currently focuses on exploring architectural and micro-architectural innovations for enterprise AI and cloud-centric workloads, with primary focus towards optimizing the core for single-thread, throughput, and compute performance. He has worked on IBM Power Processor architecture since Power 5 Plus timeline. He is one of the key contributors for the Power 10, which is going to be released in next few months. A processor, the key architecture features like instruction fusion, branch prediction, and matrix math assist. MMA, it's called in the short form. He has more than 16 plus years of experience in the area of workload characterization, microarchitecture, design exploration, compiler, code generation, and optimization, competitive evaluation, post-silicon, hardware bring up, and validation. He received MS in computer science from the Madras Institute of Technology. He's an IBM Master Inventor. He has filed more than 25 plus patents, published several papers, and delivered several talks in his field of work. With this massive, very class experience he has, there are lots, only few people in IBM, we find this kind of deep technical skills and power architecture. Satish is one of them. He is here with us, and he is going to be sharing, the workload transformation and innovations in power architecture. Satish, please go ahead and present.
Ganesan, can you please record the sessions?
Yeah, it is recorded. It is being recorded. Thank you.
Okay, thank you.
Satish,
yeah, sure. Thanks, Ganesan. Just give me 1 second. Let me just get my presentation up here.
So thank you, Satish, for accepting to deliver a talk, and we are eagerly waiting for your talk.
Yeah, sure. So actually, I'm facing some difficulty in sharing my screen. Just okay.
In the worst case, you can share the slides with me. I'll quickly share.
Yeah, just give me 1 second. Yeah, just give me a second.
Yeah, that's great. We see
got it.
We see the slides. Nice. But looks like your audio is having some problem now. No, we can't hear you. Satish, we can't hear you.
Okay, am I audible now?
Yes, 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 you are.
Okay,
Good.
there's some issue. I'll just
No
share.
problem. No problem. Take time.
Okay, good. So I hope now
Yeah, yeah. Now I can see and
my audio is also good, right?
yes,
Okay.
yes, yes, yes.
Okay. Sometimes, right, we connect to the external share through the office laptops. And sometimes the security
No
issues.
problem. No problem. No problem.
Okay, I got
Good.
it solved. So thanks
Okay.
a lot, Ganeshan, and thanks Satish, Professor Satish, for that excellent talk. You have given I think, a huge history, long history of power, like since we started the open power stuff early in 2000 timeline. So today I'm going to talk about workload transformation and innovation in power architecture. So in the past, what we used to do is we used to talk about power ISA and some of the new instructions and new features, what we have brought in into the instruction set architecture, and also try to cover the microarchitecture. So I used to get some feedbacks on that, right? So sometimes people don't get to know what actually drives these changes, right? In terms of why are we introducing this new instructions? Why are we introducing new microarchitecture into the processor core? And what exactly is the driving factor for doing that? So generally, those kind of details don't show up in the academia because it is primarily driven by the market requirement and also like the type of workloads what we are planning to run on that particular system. So there is a lot of effort goes in order to understand the characteristics of the workload, what kind of transformation we are going through in the workload space. And based on that, the entire hardware industry, right, that includes processor, memory, interconnects, and networking and storage, all these entire hardware stack actually undergoes a significant change. And all the changes are primarily driven by the requirements, the needs, what is what is triggered by some of uh, the workloads what we run on our day-to-day life, and the type of applications what we use, and how we manage things with our like banking solutions and IT solutions, and lot of such things, right? So generally, people getting that kind of view is going to be very important for students to start thinking about new innovations in this field of computer architecture, because sometimes people think maybe what more I can do in architecture, right? So we have covered a lot of things in the architecture space, but still there is a lot of scope for innovation as we see this transformation happening. So that's with a very high level background on this. Let's try to go through the slides and also have a good discussion on this topic on how these workloads are transforming and how we are actually adapting to the transformation on the hardware side, because people get to know about applications and all that stuff, but we have to translate all those things to the hardware and see how we can make our foundation better so that we can run these applications at a much faster rate, much more reliably, and also which a lot in terms of scalability also we need to have a good scalability. So I think Ganeshan gave a good introduction about me. So I basically work as a senior performance architect in IBM, and my job here is to study these workloads, understand the workloads, and see how we can influence the design of the next generation processors. That's my primary role. In the past, I have worked in bring up validation and compilers and all that space, but right now this is my primary role. And what you're going to hear a lot about Power 10 as well. I think Professor Satish discussed about Power 8. We have gone through significant changes since then, and we will be trying to cover some of the new things what is coming out in the Power 10 architecture. So let me give you a glance of the agenda, what we'll be covering. So let's start with what is actually changing right now in the field of IT, because if you look at our day-to-day life now with the pandemic showing up and all that, right, almost everyone all the way, I mean, if you start from 1-year-old kid and all the way up to like 90-year-old aged person, right, everyone relies upon IT. And certainly because of this huge needs, the IT is also going through a significant change, and we will see what kind of changes are driving this IT world. And taking that to the workloads, we will see like how the workloads are right now, what are the new workloads, what is coming out, and what is the workflow of that new workloads. Then we will touch base on some of the key building blocks of the compute infrastructure. You should be aware of this, but I want to bring it from a perspective of mapping it from the workload side to the compute infrastructure side. Then we will jump into one of the key transformation, what I will be covering, that is the related to AI, and what we should think about AI from the hardware perspective, right? There are a lot of things you might have heard from the deep learning, machine learning algorithms, and vision, speech, translation, a lot of stuff in the software field. But when it comes to the hardware side, right, how you should start thinking from a systems perspective. So that's something we will talk about. And then we will jump into this Power ISA and one of the key feature what we have put in into Power 10 and or the recent version of ISA, MMA. And then we will get a glance of what Power 10 is capable of and what kind of AI acceleration capabilities it has. So this is a broad agenda. I'll try to cover some of the topic quickly, and some topics I'll try to spend a little more time so that we can balance the time as well here. In case there are any questions, please feel free to type in the questions. I will try to get it answered at a later stage. But if things is very critical, please stop me and you can ask questions as well. Let me get started with the new era of IT and how it is defined and driven by AI and cloud. So two important aspects. Certainly this is real, and we used to have this as a kind of a concept in the past, but right now we are seeing in reality almost in our day-to-day life, both of these transformations are impacting us in all aspects. So one is AI. What AI from the hardware side, when I as a workload characterization person, right, when I look at AI, it basically helps enrich the user experience, right? That's exactly how I will define AI, because we have IT, but AI actually takes IT one step further and helps you derive a lot of insights, a lot of valuable kind of experience you can get through implementing these AI features or AI algorithms in your regular enterprise workflows or your, whatever workloads you are running. And that helps enrich the user experience. That is one critical thing what is happening in the IT field. And the second important aspect is the cloud. I think we all might have heard about this, right? Cloud, basically what it does to us is it defines and drives the next generation software design and development. We used to we used to develop software or software architecture, right? We used to develop it in one form. Right now, since cloud is emerging, it actually redefines the way we write the programs. We kind of create the software, and that actually makes a lot of changes in the way we develop code, and also we kind of create this new software for the future. And at the same time, it also redefines the deployment infrastructure, right? So the way we used to run it in the past through standalone data centers and all that, right? Right now, it's not the case. We heavily rely upon cloud and all forms of cloud, private cloud, public cloud, hybrid cloud. There are a lot of different terminologies we're hearing. But from my point of view, I just keep it very simple, right? It actually redefines the way you design and develop your software, and also how you deploy that into the infrastructure. So at a very high level, these two definitions, right? We are seeing a lot of changes in the way the code is getting executed, the type of code what is getting executed, and the stress points in the hardware that is actually getting changed. And we started thinking about various different aspects of re-engineering, or say re-engineering ourselves to kind of address those requirements for the future. That is the compute part of it. So from there, if you jump into these two areas, I'm not going to get into details. You guys might be experts in this field, right? AI and cloud. I'm not going to talk about what AI is, what cloud is, and all that, but I'm just going to show two slides. One is about AI, what is the workflow, and one is about cloud, the way the software deployment and the development infrastructure is changing, right? Those two things are very critical for us as a hardware engineers, and I would say as a computer architects, to see, right, what kind of changes that we have to bring into the architecture, microarchitecture, and all the other system components that we are interested in. So at a very high level, AI workflow basically does this, right? It actually takes data source, it creates some kind of, it prepares the data so that it can be trained, and it applies some kind of model. It could be deep learning model or a machine learning model, whatever model you think about, through later a lot of different frameworks and a lot of different software stack. But finally it does like kind of a model training, and it creates a model which can be used for inference, inferencing the input data. And the inference, what I mean is, it could be translation, it could be identifying the image, what objects are there in the image, or it could be anything, right? Detecting fraudulent checks, or like identifying any fraudulent transaction during credit cards and all that stuff. So we'll see some examples maybe in the later slide, but I'll just keep it at a very high level. So this is the kind of AI workflow what is getting embedded into our traditional enterprise architecture, right? The three-tier architecture and stuff what we used to talk about, right? The application layer, the web layer, and then the database layer. So this is actually getting into that space. And certainly it is driving a lot of changes in the compute requirements, what we have right now. And a lot of these things, we might have seen it in the past through HPC in some way, but not to this extent, but because here the requirements are a little different, and the compute requirements are certainly driving a lot of requirements from the architecture side that we have to bring in. On the cloud, I just view it like in two different forms, right? One is as I said, the way you develop the software. Certainly it is moving from monolithic to microservice, right? Because earlier we used to develop something called software in a monolithic architecture manner, which kind of clubs these user interfaces, business logic, and the data layer, which I'm showing it in the right. And given that the way the cloud is being developed and deployed, the people are moving towards more cloud native architecture, where the clients interacts through the API gateways. And you can see that the containers play a very critical role in running these microservices, and it accesses the underlying database, right? The various different databases that we use right now. So that way, the way we develop the software and deploy the software is also transforming. So putting all these things into perspective, now I'm going to merge this AI and cloud together, and we call it like AI as a service. So what happens is, a lot of these models and stuff what you are generating and using it for inference is getting deployed in the cloud. So now everything comes together, right? So we are infusing AI into the regular workflow, and also deploying it in such a way that it is consumed through the cloud infrastructure. So that is the kind of final phase that we are getting into. And a lot of companies have started doing this already, including IBM, Amazon, Microsoft, Google. There are a lot of advantages, and people are kind of debating on some disadvantages. How do we resolve it and all that? So without going into too much of details, you can just feel it like there's nothing big which has changed, but certainly the coming of AI and the way you develop the software and the way you deploy the software certainly has gone through a significant change in the recent times. So that is something that we care about, and we want to see how we can actually make sure that the workloads which are going through this change get a best experience by running it in the underlying hardware or the system stack that we are interested in. So now, putting all these things into perspective, right? I just try to show you a very simple picture of how we visualize our enterprise database three-tier architecture in the past, and how that is currently being represented in the newer generation space. You might have heard about Oracle, SAP, IBM DB2 as a classical databases which are heavily used in all the I would say very mission critical applications that include banking, trading, income tax, railway reservations, and airline bookings, and a lot of spaces. And all of these solutions are basically going to this three-tier architecture of client tier, middle tier, and the database tier. So in the past, what we used to see is like, it's all highly data centric. We used to create a lot of data and we store the data. We don't do a lot of compute on the data. Rather, we just extract the data, present it in a particular way to the user. And if you look at applications and languages, we used C, C++, Java, and we developed softwares. And traditionally, we used to have SQL databases and structured data, which are very well structured. And that's the kind of classical enterprise workload space that we were operating in the past. And as you know, the applications are highly monolithic. Now, with the transformation, what has happened is a lot of these three-tier architecture has become more of cloud native architecture. Still, it has all these tiers, but it's become more cloud native. And the infusion of AI algorithms into the enterprise workload has really increased the demand for huge compute requirements in various different forms, right? Not just CPUs, in various different forms like GPUs, ASICs, and FPGAs, and all that. Still, bandwidth and the memory bandwidth and the throughput is still critical. But because of AI coming in and a lot of things are becoming more real time, people do expect real time responses. The sensitivity towards like response time and latency has become highly critical. And at the same time, the network performance also has become very critical in the recent times because of this transformation, what is happening and the way people are using these applications. So now, certainly languages have evolved, and you can see like a lot of people use Python, Ruby, and Golang, and mix of all these things in the microservice world. And still C++, Java has a lot of importance, but doesn't mean that, I mean, there are new things which are popping up. And the databases has gone through some change, moving from SQL to NoSQL, and then structured data has become more of unstructured data. And all these monolithic applications has become more of microservice based applications. This is the kind of transformation you will see for next few years, like at least 5 to 10 years. And all of these things, slowly enterprise world is adapting to it. And finally, we will get to a place where the newer generation architecture will look more like this, what is shown in the right side. Okay. So this is the kind of a single page view of how this transformation, as we have gone through this transformation. So what is the foundation to make this transformation successful, right? So we are creating these AI algorithms, like you can see ResNet 50, ResNet 150, like 150 layers, 50 layers, and we are putting in huge compute requirements into the algorithms. And in the past, it was not possible because we did not have compute capability to do that. But right now it is becoming possible because we do have a lot of compute capabilities, which is coming in through various different type of hardware that we generate. So basically, if you look at the foundation to make this cloud transformation, to make this AI transformation successful, is relying upon this underlying compute infrastructure. Okay, so that is basically driven by the semiconductor world, and it starts from the CPU architecture, microarchitecture. It includes a lot of accelerators like GPUs, domain-specific accelerators, and FPGAs is also getting a lot of traction. Memory plays a very critical role, and it is also going through a lot of innovations in the recent past. You might have heard about 3D crosspoints, Intel Optane technologies, and there are a lot of innovation happening in that space. And interconnect is also going through a significant change compared to how we used to view interconnect in the past. Storage and networking is also kind of becoming very critical, and transformation is happening in those spaces as well. So as a whole, if you really look at it, the semiconductor industry is really kind of going through a significant advancements in the last 5 years, I would say, and it is going to continue for next few years till we kind of mature these technologies and get it into good shape to address all the requirements of this workload. So basically, this is how the flow is, right? So you study the workload, you understand how the workload is transforming, and then you go in and innovate in the semiconductor world on how we can fulfill the requirements, what is being imposed by these workloads. And if you look at it, these are the kind of changes that we run into. And today we will be mainly focusing on the CPU side, okay? Because it's a broad topic, obviously we cannot cover all of this. But one thing you need to remember is, the important thing what has also changed in parallel to this is like the hardware is also becoming more open. You might not have sensed it in the past. If I mean, during my time when I was doing my college, I mean, when I was graduating and all, right, hardware is more proprietary. There's no way, like we were not talking about, we were not at all talking about like any openness in the hardware. But in the recent times, right, you can see like all of these areas, we have an open reference architecture that is coming out, not just from like open power side. I'm saying in general, there is a lot of initiative which is happening in order to make this hardware area more open, with open compute, with open power, and even a lot of people are like contributing to this space in order to create a more of a open-ended architecture, so that it creates more transparency as well as more control for innovation from the academia, research, and all that space, right? So that's something we should keep in mind. And then now we will get into the AI space in little more detail. And today we are not going to cover cloud and what kind of innovation has happened in the architecture in cloud. In the interest of time, we'll be talking only about the AI and how Power ISA has evolved to kind of adapt this AI stuff, and what kind of implementation we have put in the Power 10 in order to fulfill these AI requirements for the future enterprise needs. On the AI front, if you go a little bit deeper, as I said, it is impacting all across the stack, right? All the way from CMOS technology, devices, chip, algorithms, applications, everything is going through a significant change. Just if you focus on the chip and device and some of the algorithm characteristics, right? It basically like the processing of unstructured data and like a huge, bigger size data like videos, images, and voices. These things are happening at a very large pace. The second thing is like this puts a lot of requirements on linear algebraic operations and such as tensor processing, and though the control flow is relatively simple in some of the machine learning algorithms, you do see the importance of control flow as well. So when I say control flow, it's more about branch predictions and all that stuff, right? What we talk about in the architecture world. The algorithms like say the gradient boosting machines and all that do have a lot of sensitivity to some of the control flow environment as well. And then all of these parameters are like really huge, and it imposes a lot of requirements for storage, for high bandwidth, for low latency memory access, and put together, right? All of these things is we really want the data to be very close to the compute, and the near memory computation and data reuse is also kind of becoming very prevalent. So if you look at AI at a very high level algorithmically, maybe we will not see we'll not see that, okay, I'm running it in a processor, I'm running it in my system, what's the problem, right? So, but underneath, if you go one level deeper and if you start looking into it, certainly there is a significant change that has to go into your even laptops or even your mobile phones or even the big servers, what I'm talking about here. All of these things has to change. So now, where these changes can go in, right? So if I'm talking about AI compute requirement, there are like multiple options we have, right? So we can put in more acceleration on the CPU. We can actually put in more acceleration through GPUs, and FPGAs can play a role, and we can define ASICs, right? Application specific circuits in order to fulfill that. If you look at the diagram, what I'm showing here, right? CPUs are much more flexible. And it is a general purpose thing, and you do a lot of regular tasks, and you can embed a lot of AI tasks into your regular task, and you can still do a lot of inferencing and a lot of your tasks through CPUs. But when you go for like a very huge push in terms of like training the models and like kind of digesting a lot of these data, right? Like YouTube videos and all that stuff, if you want to digest offline, certainly you need like huge compute, and CPUs may not be fulfilling that requirement. So you need to go in for a special purpose hardware like GPUs, FPGAs, and ASICs, which will eventually help you solve that problem. And some of these things are really applicable for automation, not for automobile industries and robotics and all that space. Also, we do deploy some of these things to make cars more intelligent, to make robots more intelligent, and all that. So both from the server side, from the automobile side, or any space you take, right? All these chips play a very critical role. So today, from the power side, now we are getting into the topic of Power ISA and matrix matrices thing, what we are going to talk about. And this is primarily going to cover the AI acceleration on CPU, right? So a lot of efforts are happening. You might have heard about NVIDIA, you might have heard about a lot of startups coming in the AI space, like Habana, Grok, Graphcos, and a lot of names you might have heard. They are doing like AI acceleration chips. At the same time, if you look at from the CPU standpoint, if you ask me, I can name two companies who are like has got inbuilt acceleration capabilities to architecture. Maybe we can put it that way, right? One is Intel has pushed a lot of ground in this space through their AVX 512 infrastructure, and they are putting in more and more capabilities on their CPU cores in order to accelerate the AI task. And Power architecture is also kind of evolving a lot in this space to kind of bring in the AI capabilities into their architecture, as well as implementing the same in their microarchitecture. So these two, IBM and Intel, are like right now playing a very critical role in CPU centric AI acceleration space. But other than that, if you go off chip or other than CPU, there may be other companies you might be hearing about. And power side of it is more open, and we are like ISA is open, and we have a lot of open reference microarchitecture that has been published to the external community. And at the same time, going forward, more I mean, even some of the implementations also we might be getting. So still not confirmed, but at least some part of it might become open in future as well. So, so from given that, from there, right, if you jump into some quick ISA examples, right, Power ISA is one, RISC-V is another one, Spark, IA32, IA64 ARM, some of the classic known ISAs. And ISAs basically defines the architecture. I don't want to explain the difference between what is architecture and microarchitecture. Certainly you guys in your curriculum, you might have read about that. ISA defines more of the interface between the programmers and the hardware, through which the programmers can issue these instructions and then like leverage the hardware capability, what is being implemented. That implementation is more like microarchitecture, and the interface is defined as instruction set architecture. So that's how we view it. And Power ISA has a long history, right? 30 years of history, I would say. All the way from 1985 till 2020, it is still sustained. It's sustaining innovation and bringing in all the new capabilities and the requirements, what is needed in order to fulfill the workload demands and the market demands, right? So that way, and it has become open long back through power.org initiative, and then now the open power is part of the regular Linux Foundation, right? So that way it has become very much open, I would say, and we don't have any licensing requirements in order to use this architecture. So now, in terms of power architecture and the Power ISA, the recent version is Power ISA 3.1. And you might see like a lot of new features that has got introduced into the Power ISA version 3.1. And to name some of those things, right? Prefix architecture is one such thing. Then we have got these new instructions and data types that we support primarily in order to fulfill the AI requirements. And then we have like quite a few enhancements in order to address the cloud security in cloud, then some kind of power management related things, and also some kind of system features and ease of use related activities. So these are some of the high features, right, that we would like to highlight as part of version 3.1, where we have brought in some innovation. So just to talk quickly about the prefix architecture, traditionally Power is like a 32-bit ISA. All the instructions are of 32-bit size. So with the introduction of prefix architecture, it now becomes like 64-bit. So there is a lot of scope for expansion in future. We can bring in more instructions. We also have introduced some kind of masking capabilities and all that. I'm not going to go into the details. I'll leave it to you guys to go and look at Power ISA document to see what prefix architecture is in more detail. And at a very high level, this is like expanding our capability in terms of instruction word size. So traditionally we are like 32-bit, and now we're getting into more 64-bit size. And in terms of new instructions and data types, we have got a lot of SIMD expansions. And at the same time, we have got this new feature called MMA, what is called Matrix Math Assist. And that supports wide variety of data types, all the way from double precision, single precision, half precision. We also support bfloat 16, and then int 16, int 8, and int 4, right? So still research is happening on how do we exploit int 4 data types for inferencing and all that, but still we do have that capability in the ISA right now with the ISA version 3.1. So a lot of these innovations has gone in. So let's take a little more deeper look into what this MMA is about. So basically, MMA architecture is nothing but a matrix multiply assist instruction architecture. So with this introduction of this, with the introduction of these new architecture, right, you have like a single instruction which can help you do a matrix multiply type operation, right? So earlier we used to go through your own, like through the regular floating point multiply add instruction, you have to do a lot of compute, and you have to like do splats and a lot of stuff in order to get the matrix multiplication done. We felt like matrix multiplication is becoming a very dominant and also a very prevalent thing, what is happening across workloads, across domains, across industries. So that way, this is going to be going to be like something the default thing for future. So that way, this particular matrix multiply architecture is going to play a critical role for most of the applications in future. So in a way, it actually accelerates a lot of dense numerical linear algebraic computations. I'll give one example of how this operates in the Power ISA context in the next couple of slides, and then I'll quickly talk about what kind of implementation we have for this on Power 10 processor. And there is a lot of scope for innovation. This is just like a starting point, I would say, right? Because within matrix multiplication, there are a lot of like cases that we have to deal with, like sparse matrix, like matrix vector computations, and a lot of stuff. So matrix MMA is more to deal with matrix multiplication at this moment, and it operates very well for the dense matrices. It does good for sparse as well, but it doesn't have any special feature to handle the sparse matrix formats that that we use. So that way, this is the foundational piece that we have put into the Power ISA to support the future requirements. So not in terms of data types, in terms of compute instructions, right? Data types, it supports, as I said, it supports double precision, it supports single precision, it supports half precision and before 16, and also different forms of integer data types, right? From 16-bit to 4-bit. That's the type of data type. Those are the data types it supports. In terms of compute instructions, we do have like 5 category of instructions, each one to deal with one particular data type. And also we have introduced something called lane masking, so that we can mask certain compute and avoid certain computation within the instruction and generate only partial results in case if you have that requirement. So those are some that's a kind of quick view of how these instructions operate in the real world. This picture I just spent like a couple of minutes, right, so that you get a view of how we actually do this computation in hardware. So basically, we are not expanding our register file size. If you know x86 and if you look at power supports the vectorization of power. The vectorization length is 128-bit. That means it can support 4 single precision operation in a single instruction, and or 2 double precision in a single instruction. And if you look at like x86 architecture, is more like AVX 512, so it supports 512-bit. If you look at it from an external point of view, it might look like, okay, 512 looks bigger than 128. But with this innovation, what we have put in here, even with 128-bit architecture, we are able to generate the same level of compute capability as 512-bit, right? Without complicating the hardware too much, right? We have not expanded the register file. That way, we are able to save power. We are able to save space. The real estate is very, very critical, given that we are running out of the technology innovation. Once we move to like 7 nanometer and 5 nanometer, post that, it's like really tough to get more space in the chip. And obviously, power is also another factor that we have to keep in mind. So with all that, with 128-bit architecture, we are in a position, we are able to generate 512-bit results. So for matrix, what we do, matrix multiplication, what we do is the instruction what we have introduced, take 228-bit values and it try to generate a 512-bit result. So what happens is we have like, let's assume this is a single precision matrix operation, and you are taking 4 inputs on one side, another 4 input on the other side. So each of this 32-bit value gets multiplied by each of the values in the other side, and it generates like 4 results. Similarly, each element of 32-bit value gets multiplied by each other element on the other side. And as a whole, you generate 16 32-bit results, and that you keep accumulating into a 512-bit register. So basically what we did in order to handle this 512-bit result, you might ask, right, how you will hold the 512-bit results now, since our register file size is only 128-bit. So the solution is pretty simple. We mapped 428-bit register to represent one 512-bit register or a value. So that way the result gets into 4 different 128-bit register file. So that way you can operate those values separately or as a whole as a one single value as well, right? So that way we were able to kind of address the output requirement as well, and we were able to do this for various different data types. That includes up all the way up to 8-byte, right? So here the 8-byte, the way the 8-bit instruction operates, right, is shown in the figure in the right. So there you take like each of the element and multiply and sum all these values within this component and generate a 32-bit value. And similarly, you take four elements and multiply here, and then you sum it, and then you generate a 512-bit value. So if you look at the way the instruction operates in the instruction set manual, you will be able to see how this works in a much clearer way. So that's the 8-bit MMA 8-bit instruction. And I know all of you know matrix multiplication. My intent is not to explain you what matrix multiplication is, but just to give a preview. This is what we do in matrix multiplication. We take one row and then one column. You multiply each element here to each element in this column, and then you generate one value, right? That's what you do in matrix multiplication. And what we do in outer product operation is you take one block of transposed A matrix, and you take one block of B matrix, and then you multiply this with this, and you generate one block of result. This is what we do in the outer product operation. And how we are accomplishing this with MMA instruction is very simple, right? You take the same one block, you take the values, say 1, 9, 17, 25 into one register, and AA, AB, AC, AD into another register. You just execute one instruction. It generates like 16 results. That is nothing but one AA, one AB, one AC, one AD, and it goes all the way up to like say final this 25 AD, this multiplied by this generates total of 16 results, what is shown in the bottom here in the boxes. And you just keep shifting and then go one by one element, and you load four values here, four values from here, and you keep doing this. You will be able to generate these results, right? So from a very high level view, it might look like, okay, very simple instruction, but still that's very, very powerful. It with just like 1, 2, 3, 4, 5, 8 instructions, right? You will be able to generate like one block of results. So that way you just shift these blocks and you will be able to generate this full results in just a few instructions, as against how you used to do it in the past. So this literally gave like a significant boost in terms of performance. We have demonstrated the performance capability of Power 10, right? It gives you up to 10x improvement at a socket level, and then up to 20-25x, goes up to all the way up to 20-25x improvement, right? We're talking about X factor here, not like the percentage factor, right? So the X factor is really huge, and that's the level of improvement that you could expect, right, when you go to the Power 10 type processor, moving from Power 9 to Power 10. So let's take a quick view of what Power 10 is capable of in terms of implementing this particular architecture feature, right, that I have mentioned in the previous few slides. So this gives you an overview of the power processor technology roadmap. All the way from Power 7, and we are working on Power 11 right now. And as Professor said, you are using Power 8 family of processors. And right now we are going to GA Power 10 family of systems. And then maybe in future, you will see Power 11 family of systems, right? So here, this Power 10 is where we have introduced all these AI optimized ISAs and the cloud specific security features and all that. And if you get a little bit deeper into the Power core, that Power 10 core, right, it gives you a significant performance boost. And the AI infusion, right, we have done it in like two different ways. One is 4 times the matrix SIMD acceleration capability. What does it mean is like you have like a dedicated units which can do matrix acceleration, and that actually at a core level, it increases your compute capability by up to 4x. And then the regular SIMD also has gone through a significant change. That means you are doubling the capability of regular SIMD. This is over and above the accelerator what we have put in on the core, right? So that picture you will get very clearly in the next slide when I show you that. And it actually supports up to 30 SMT8 cores, and it supports up to 60 SMT4 cores in a single chip. So I think Professor mentioned about 8 cores in Power 8. So we have made a lot of improvements from there. And now with Power 10, right, you can see up to 60 cores in a single chip. So that is a huge advancement. And actually, I would say it's very like the whole processor industry is like very competitive, and we are like really fighting this this game very well at the moment, with 60 cores in a single chip. With, if you put like 4 sockets, you get like say 240 cores. That's really huge, and you can do a lot of tasks with those cores, and that too with on inbuilt AI acceleration on that. Right, this is a microarchitecture view of the Power 10 core. So what I was talking about, this MMA accelerator, right? So these are the regular SIMD units. So earlier we used to have in Power 9 only 2 such 128-bit units, but right now we doubled it. So that way we can support 4 regular SIMD operation every cycle. And in parallel, you can also do like say 2 MMA instruction or MMA instructions every cycle, right? So you can generate 2 512-bit capability. So as a whole, I mean, you cannot do all things in parallel, but certainly this along with 2 execution slices here can be done. And then there is some issue level things that we have put in order to make sure the bandwidth is balanced for the loads and store ports as well. So that way there is a huge FP compute capability. And remember, this MMA accelerator is not just for lower precision, it supports double precision and single precision, right? That way all the HPC needs will also get fulfilled, right? In terms of the benchmarks what Professor has shown in the previous slide, right? A lot of those benchmarks, including LinPack, including DGEMS and all that stuff, can run at a much faster rate in the P10. So if your application has such demands, then it's not just only for AI, which is lower precision, it is also for regular HPC type precision compute, I would say, because AI is more like we compromise on precision. We don't care too much about precision, but when it goes to HPC, we care a lot about precision. So it actually does precision compute, we can put it that way. And that too, with that acceleration capability, it's really going to be very huge. And in terms of bandwidth, so this doesn't come for free, because you put that much of compute into your core, right? You also need to balance your memory subsystem. You need to load so much of data in order to do that compute, right? So we have to double the load bandwidths across all different cache levels, and all the way up to the memory. And the bandwidth has really grown, and we support 4 32-byte loads and 2 32-byte stores at SMT8 core level, and SMT4 core level it will be like 2 32-byte loads and one 32-byte store. That level of load bandwidth capability is what we offer in the power systems right now. And that actually coupled with 4 times the matrix math 4x the matrix math acceleration support, with 4 units sitting in there, and 2 times the bandwidth for the 8 independent SIMD engines per core, right? That's also coming in as part of a single core that we talk about. And that's exactly what the Power 10 core will look like from the AI compute. And obviously that is being supported by a huge bandwidth, which is traditionally IBM power systems used to have huge bandwidth, and we used to maintain that legacy in this Power 10 system as well. Okay, I'm not going to spend a lot of time in this slide because we spoke a lot about this, and I think I tried to cover my 45 minutes, and mostly I think I'm on time. So one thought before we close the session for today, right? Again, I'm bringing in the concept of openness, right? Which is very critical, because a lot of these innovations can go in. And if you look at a lot of the new accelerator companies, right, they're putting in a lot of innovations, but you don't get to know about, like, even like it's very tough to read even the ISAs for some of these specific accelerators, what is coming out from different startups and all that. So openness is something very important, and we need to keep that going in order to make the whole computer industry evolve and grow at a much faster rate. And that's very critical for future. And I think certainly from that perspective, power, I think RISC architecture, and all of these people are putting a lot of effort in order to make this whole industry, right, become more open and bring in more innovation, just like what the revolution we had on the open source with GNU and Linux playing a critical role in the software side, right? So right now it's become mainline, and that's what we use. Red Hat has become more like the classic enterprise server what we use. So similarly, going forward, we will be seeing more open hardware being built and being used by various different HPC teams, as well as all the academias can build their own cloud infrastructure and all that with the open hardware infrastructure. So that way, the entire stack, all the way from core, memory, interconnects, the storage subsystem, the IO subsystem, networking, everything has to become open. That way, I think we'll have a much better path for innovation for future. So with that thought, I'd like to close the session for today, and I'll hand it back to Ganeshan, and I'll try to address the questions as we talk, maybe as we go through the next session in the interest of time over the chat window.
Satish, thank you very much for the very detailed and kind of, like, I think looks like, whatever you presented, shows your experience. And it's very important that, the people who are all attending this session certainly, will take, we would have learned, a lot of things. Even some people already WhatsApping me, about the session and all. It's very good. And we got nearly 86 people as part of this program. And, certainly, international, there are a lot of people from Europe and some people from US also joined. So it's a good presentation, Satish, overall. Thank you very much.
Thanks, Ganeshan.
And there are some questions on the, the chat window. You can take care, by.
Yeah, sure. I'll try to address as we make progress with the other sessions.
Thank you. Thank you.
So Satish, there is a question like performance measurement with respect to which parameter he is asking. Kriti Gupta, he or she.
So so right now the way we are reporting performance for Power 10 is reference to Power 9 capabilities, what we have got, and it is in terms of flops and also in terms of the sustainable flops, I would say, right? What we could sustain in terms of the flop rate, what we could accomplish for some of this critical operation. That's the way we are measuring it at a socket level. And that's the number I gave, right? The 10x improvement with the core count increasing, slight improvement in frequency, and the 4x compute capability, what is coming in as part of the core. And
so I'm sorry to interrupt, but the context of the question was something different, I guess. Like they wrote, like, I wanted to know, like, if I'm measuring the performance of EDMA and Ethernet IP, the source and destination will be a memory to SPA or I2C. So the transfer of data is communicating to whom or where it is going.
Okay. So, maybe I think I'll probably take that question offline.
Right.
I think I didn't get that question properly, but certainly we'll talk over chat.
Right. There is another question.
Sure.
What is IP behavior, and can you suggest some sources to learn IP behaviors?
Yeah. Okay. Sure. I'll probably point to some of the open IPs.
You can text, I think, later. So
okay.
You can text these things later. So what are the solutions of AI infused bandwidth and compute on edge devices?
Okay. Yeah. Okay. That's a good question. So yes. So I think I'll try to address that over text, but quickly, right? All the things what I have talked about is in the server side, not on the edge side. So certainly there are a lot of things coming out. And we don't, at least from the power side, right? What we build is only for the server infrastructure, not for the edge infrastructure. So I think innovations are happening on the edge side around ARM IPs and Intel IPs as well, but we are not playing a very critical role. But if we're talking about edge, like say 5G, kind of compute at the edge, then that's certainly some place where servers do play a role, right? That's what the things what you installed on the edge as a servers. So that type of thing certainly can get accelerated with this type of innovation. But here it's more about server side innovation what we are dealing with. Yeah.
There is another question. I think we are running out of time now. So maybe you can go through the chat and respond to all the remaining questions.
Yeah, I'll do that.
Meanwhile, we'll start the next session.
Sure. Thanks, Professor.
Thank you, Satish.
Thank you, Professor Satish, for handling that. I know there are a bunch of questions also. on the chat window. It's getting filled up. Thank you. And we are almost nearing 90 minutes since our workshop started, and actively people are there. A lot of participants still very active and asking questions, and this is the momentum we want for all these kind of the technology based workshops. Thank you very much for the participants asking questions too. Definitely there is an opportunity for you to speak in our next workshop maybe with IIT Roorkee or the other place